You've probably heard the headlines. Quantum computers will break all encryption. They'll revolutionize drug discovery. They'll solve all problems that would take classical computers longer than the age of the universe. And technically, some of that is true, but there's a massive gap between what quantum computers can theoretically do and what they can actually do today. This gap isn't just a minor inconvenience, it represents fundamental physics problems that brilliant researchers have been battling for decades. Today we're going to explore exactly what those limitations are, why they exist, and what it will take to overcome them. First, let's quickly understand what makes quantum computers special. A classical bit is either 0 or 1. That's it. But a qubit can exist in a superposition. It's both 0 and 1 simultaneously until you measure it. This property, combined with entanglement, theoretically allows quantum computers to explore many solutions at once. With just 300 qubits, you could theoretically represent more states than there are atoms in the observable universe. That's the promise. Now let's talk about why we can't cash that check yet. There are 5 major limitations we need to understand: decoherence, error rates, scalability challenges, algorithmic limitations, and extreme physical requirements. Each one represents a fundamental barrier between where quantum computing is today and where it needs to be. Imagine trying to balance a pencil on its tip. For a brief moment, it stands perfectly upright, then gravity, air currents, and tiny vibrations cause it to fall. A qubit faces the same problem, except the forces trying to knock it over are everywhere and relentless. This is decoherence. The quantum state of a qubit is incredibly fragile. Any interaction with the environment, heat, electromagnetic radiation, vibrations, even stray particles, causes the qubit to lose its quantum properties and collapse into a classical state. Here's the terrifying part. The best superconducting qubits today maintain coherence for about 100 microseconds. That's 1/10,000th of a second. In that tiny window, you need to perform all your quantum operations before the qubit forgets what it was doing. To run meaningful quantum algorithms, you might need millions or billions of operations. But with only microseconds of coherence time, you can barely get through a few thousand. It's like trying to write a novel, but your paper dissolves after every sentence. Everything in the environment is trying to measure your qubit. Thermal noise from any temperature above absolute zero, electromagnetic fields from nearby electronics, even cosmic rays passing through the lab. Every single interaction is another chance for decoherence. Physicists measure 2 types of coherence time. T1 is how long before the qubit loses energy and falls back to the ground state. T2 is how long the qubit maintains its phase information. Both need to be long enough for your algorithm to complete, and T2 is almost always shorter than T1. So the first major limitation is clear. Every quantum computation is a race against time, and time is not on our side. Even if qubits didn't decohere, we would still have a massive problem. Quantum gates, the operations we perform on qubits, are not perfect. Not even close. A classical transistor might fail once in 10 to the 17th operations. That's 100 quadrillion operations between errors. A quantum gate? We're lucky to get 100 operations before something goes wrong. That's a gap of about 14 orders of magnitude. Quantum errors come in 3 main flavors: bit flip errors where 0 becomes a 1 or vice versa, phase flip errors where the quantum phase gets inverted, and depolarizing errors which randomly apply any combination of errors. Real quantum systems experience all of these simultaneously. Here's why this matters. Errors accumulate. If each gate has 1% error rate and you chain together 100 gates, your result is basically random noise. Any useful quantum algorithm needs thousands or millions of gates. Without error correction, the output is meaningless. The solution is quantum error correction. You use multiple physical qubits to encode a single logical qubit, and clever encoding schemes let you detect and fix errors. But here's the catch. Current estimates suggest you need about 1,000 physical qubits for every logical qubit. Suddenly, a useful 1,000 qubit quantum computer requires 1,000,000 physical qubits. There's a crucial concept called the threshold theorem. If your physical error rate is below a certain threshold, about 1% for most schemes, then adding more qubits for error correction actually helps. But if you're above that threshold, adding more qubits makes things worse. Current systems are just barely crossing this threshold. This is why we're in what's called the NISQ era, noisy intermediate scale quantum. We have enough qubits to do interesting experiments, but too much noise for practical applications. We're stuck in the middle ground where quantum advantage is possible only for very specific, carefully chosen problems. Let's talk about building bigger quantum computers. You might think it's like building classical computers, just add more transistors, but quantum systems don't work that way. Every additional qubit makes the entire system exponentially harder to control. First, there's the connectivity problem. Ideally, any qubit should be able to interact with any other qubit, but in real hardware, qubits can only talk to their neighbors. To run an operation between distant qubits, you need to shuttle information across the chip using swap operations. Each swap introduces more errors and takes precious coherence time. Then there's the temperature. Superconducting qubits need to operate at about 15 millikelvin. That's like 0.015 degrees above absolute zero. For reference, outer space is about 3 Kelvin. These quantum computers are literally colder than the void between galaxies. Maintaining this temperature requires a dilution refrigerator, a room-sized apparatus that costs millions of dollars and consumes tens of kilowatts of power. Every time you want to modify the hardware, you need to warm it up for days, make your changes, and spend another day or two cooling it back down. As you add more qubits, crosstalk becomes a nightmare. The control signals for one qubit can accidentally affect its neighbors. Shielding helps, but perfect isolation is impossible. More qubits means more opportunities for interference. Each qubit requires multiple control lines, readout channels, and precise calibration. A 1,000 qubit system needs thousands of microwave cables, each carefully engineered to work at millikelvin temperatures. The control electronics alone fill multiple equipment racks. The solution might be modular quantum computing, building smaller quantum processors and connecting them. But quantum information can't simply be copied like classical data. Creating reliable quantum links between modules is itself a massive unsolved problem. Here's something that doesn't get enough attention. Even with perfect, error-free quantum computers, they won't solve every problem faster. Quantum speedup only works for specific types of problems. Shor's algorithm can factor integers exponentially faster. That's real. Grover's algorithm provides a quadratic speedup for searching. Quantum simulation of molecules could be revolutionary, but for general computation, your laptop will remain faster than any quantum computer for the foreseeable future. Take Grover's algorithm. It searches an unsorted database with the square root of the steps. Sounds amazing? But quantum operations are thousands of times slower than classical ones. A quadratic speedup doesn't help if each operation takes 1,000 times longer. You need problems where the exponential or super exponential speedup overcomes the massive per operation overhead. There's also the input-output problem. Quantum computers need classical data to be encoded into quantum states, and results need to be measured back into classical form. These conversions are inherently slow. If your algorithm spends more time on I/O than actual computation, the quantum speedup disappears. What's the point of it? From a theoretical perspective, the class of problems quantum computers can solve efficiently, called BQP, is not believed to contain NP-complete problems. The traveling salesman problem, satisfiability, and many other hard optimization problems probably won't yield to quantum attacks. Quantum computers are powerful, but they're not magic. And there's a sobering thought. Truly powerful quantum algorithms are rare. Shor's algorithm came in 1994, Grover's in 1996. Since then, new algorithmic breakthroughs have been incremental. We might have already discovered most of the problems where quantum computers shine. So where does this leave us? Is quantum computing a dead end? Absolutely not. But we need to be realistic about the timeline and the challenges ahead. Progress is happening, qubit counts are growing, coherence times are improving, gate fidelities are getting better, but we're still far from fault-tolerant quantum computing. Error correction remains the biggest hurdle. Multiple approaches are being pursued. Superconducting qubits lead today, but trapped ions offer higher fidelity. Photonic systems could work at room temperature. Topological qubits might be inherently error-resistant. Neutral atom systems promise scalability. The winning technology might not even exist yet. Most experts estimate we're 10 to 20 years from fault-tolerant quantum computers that can outperform classical machines on practical problems. That's not a failure. That's the reality of building fundamentally new technology. Just take the transistor, for example. The transistor took decades to go from laboratory curiosity to world-changing technology. Alright, that's all I got for y'all today. Thank y'all for watching. The quantum revolution is real. It's coming. It's just going to take a bit longer than the headlines suggest.